The system stability is very important to ensure the normal operation of a circuit. In this lecture, we are going to learn what kind of system is stable and also how can we analyze the stability of a typical system. So first, we'll begin with a negative feedback. So let's first plot a typical negative feedback system. So in a typical power electronic converter, negative feedback is necessary to ensure the closed loop control of the output signal, right? So we use a block, a rectangular block to represent a typical system. And let's denote the input is here, output is here. Output is denoted as Y, S. And this block is represented by a transfer function which is marked as H, S. And to construct a closed loop control, we need to introduce the negative feedback, right? So basically here is the output signal. Negative feedback means we sense the output signal using a signal sensor whose signal gain equals to beta. So therefore, the output of this sensor will be equals to beta times Ys. Then we feed this sensed output signal into the input port by introducing a block, so which calculate the difference between the reference signal. Here is the input reference signal. And the sensed output signal. So basically, this is a subtraction calculator which calculate input signal xs minus beta ys. So the signal here we can obtain is equal to xs minus beta ys. So therefore, because the input of this block is xs minus ys, the gain for this stage is is hs, so that we can calculate the relationship between ys and xs minus beta ys. So we would have such a equation that ys equals to hs times input here, xs minus beta ys. And we can break the bracket to expand this right-hand side. So the result will be hs xs minus beta times hs ys. See that this equation contains only input xs and output ys of the closed loop negative feedback system. So we can calculate the ratio between ys and xs. So by moving this y part to the left-hand side and keep the x part in the right-hand side, we can manipulate the equation to find out this ratio. This ratio will be equal to hs over 1 plus beta hs. And this is a very important equation. So we have multiple quantities here, right? First quantity here is y over x, the entire output divided by input. So we call this as closed loop gain. And if we look at the right-hand side, there are another two quantities, right? One is HS. So HS, if you look here, it is like we consider we do not have this negative feedback. The output over input will be HS. So we call this as open loop gain. And another one is beta times HS. Beta times HS is kind of the gain through this closed loop. So we call this as loop gain. So those three critical quantities are important for us to judge the stability of the system. So based on this formula, we can see that the closed loop gain equals to open loop gain divided by 1 plus loop gain. Okay, next, let's look at one very basic criteria to judge the stability of the closed loop system. So this criteria is called the Barkhausen's criteria. So there is one special scenario in Barkhausen's criteria. If the denominator here equals to 0 at one specific frequency, omega 1, right? So for example, we write it as if the beta HS s equals to j omega 1 equals to minus 1. So this means that the denominator of the closed loop gain equals 0. So the closed loop gain will approach to infinity. So then closed loop gain will approach infinity. So this means that considering the input always contains white noise with different frequencies. If there is a noise signal at the frequency omega 1, right, we call this as ambient noise. Then this ambient noise will be amplified by infinity times. So this will introduce oscillation at this specific frequency. So introduce oscillation at this specific frequency. This means that the system is unstable. And there is another scenario in Barkhausen's criteria, which corresponds to the case if the phase angle of the loop gain beta S equals to J omega 1 means the phase angle of loop gain at one specific frequency at omega 1 equals to minus 180 degree. And we look at the amplitude of the loop gain. Suppose the amplitude of loop gain at this frequency is bigger than unity. For these scenarios, minus 180 degree, right? From here to here, minus 180 degree. Going through this calculator, another minus 180 degree because of the minus sign. Together, it's kind of 360 phase shift. In the loop. So this means we will introduce positive feedback. Although we have minor sign, but due to the phase shift of loop gain, we will have a positive feedback. Now if we look at the amplitude condition, the amplitude is bigger than 1, right? This means that the loop noise at omega 1 would be amplified. So for one loop, positive feedback amplified by beta h times bigger than 1. And for again, the signal will run again and again within this loop. Each time it is amplified by a larger than 1 times. With many, many times, this signal will accumulate to a very large value. So this means that we would have oscillation at omega 1. And this oscillation would be always be amplified each time it goes through the loop, right? So this means the system is also unstable. So for this condition, to summarize, we consider that the unstable system will means that two conditions, right? First condition is that the phase angle of loop gain at one specific frequency equals to 180 degree. This establishes the positive feedback. And the second condition is that the amplitude for the loop gain at this frequency is bigger or equal to unity. Or we usually refer to 0 dB in decibel representation. So those are equivalent to the statement that the system is unstable. Now to summarize, right? To summarize our discussion here, so basically we can conclude that oscillation happens at omega 1 if two conditions, right? First, the phase shift at this frequency is too much, sufficiently large, right? Such that the feedback becomes positive. And second condition is that the loop gain at omega 1 is sufficiently large sufficient to allow signal build up Okay, so this means that there are two scenarios, right? One is that if the amplitude is bigger than 1, meaning each loop, the signal is amplified, right? If the amplitude equals to 1, which will correspond to this condition, meaning that the denominator equals to 0, which corresponds to an infinity closed loop gain. Both cases correspond to unstable system. So this description kind of summarizes the unstable conditions for a closed loop system. In this section, we use the typical negative feedback system as an example to introduce the conditions for the unstable system. And also we introduced the Barkhausen's criteria, which is a very classic standard to determine the stability of a closed loop system. And next section, we are going to specifically analyze the condition for a stable system.